Alright, welcome to the chapter 3, okay, for organic chemistry. Alright, so you can see we have completed chapter 1, the atoms, the building block of matters. Then we have gone through the chapter 2, talking about how the atoms actually bond together, okay, to form a molecule or ionic compound. Okay, and the third chapter now, we are going to concentrate more towards the molecules, okay, which means that they are covalently bonded, okay, between the atoms to form the molecules, yeah. So the molecules can be either, most of the hydrocarbon we're going to talk about here is going to be non-polar covalent bonds, of course. When we're talking about functional groups, okay, then you'll be polar covalent bonds here, okay. I'm going to describe more on that. Okay, so for chapter 3, the content will be spanned through week 3 and week 4, okay, will be week 3 and week 4. Okay, let's start with the chapter 3, okay, hydrocarbons, alkanes, alkenes, and alkynes, yeah. So what is the objective of this chapter, okay, is to show that you understand the general importance of organic chemical compounds. Then you can explain the difference between inorganic and organic compounds, okay. So because this chapter, food molecules, we're going to concentrate on organic compounds here, okay. Then you need to know, okay, learn how to write the condensed and expanded structure formula for compounds, okay, representing it. Then classify the alkenes and normal or branch. This is very important, okay. Assign the IUPAC naming and draw the structural formula for alkenes, yeah. This is one of the key areas that you will be tested, okay. Then describe the key physical properties of alkenes. This is very important, yeah. Understanding the physical properties allow you to control. Okay, in chemical it's all about knowing how to control the molecules, yeah. And a lot of them is the difference in the physical properties. Alright. Physical properties includes like melting point, boiling points, solubility, and so forth, yeah. Then the name and draw the structural formula for the geometric isomers of the cycloalkenes. Okay, the alkenes and cycloalkenes are very similar. Then classify the unsaturated hydrocarbon as alkene, alkyne, or aromatics. Write the IUPAC name for the alkenes and alkynes. Okay, namings. Predicts the existence of cis and trans isomers, classify the organic compounds and aliphatic or aromatics. Okay, aliphatic is straight chain, aromatic is the ring form. Recognize uses for specific aromatic compounds, and then know about the key physical properties here of alkene, alkynes, and aromatic compounds. Okay, let's start with the week 3 contents. Okay, for week 3 contents, we will talk about 3.1, 3.2, 3.3, and 3.4 here. So we're going to talk about carbons, talk about the functional groups in general, then we're going to concentrate in alkenes and cycloalkenes here. These are related, okay. Okay, let's look at the first one, carbons. Carbon is the elements of organic compounds. Okay, you realize that the organic compounds, the main structural component is carbons. Okay, and why do we concentrate in the organic compounds in chemical? Okay, it's because food components is made of these three things: carbohydrates, proteins, and lipids. These are the major components that are made up of food. Correct or not? Okay, it's either carbohydrates, proteins, or lipids. Alright. Of course, you will go deeper in that. Yeah. Okay. You will see that from semester 1 to semester 6, you are always encounter these three things: carbohydrate, proteins, and lipids. But okay, different subject will points towards the different properties or different the areas of these three components. Okay, for organic chemistry in this subject, I'm going to teach you the fundamental knowledge that pertain for these three components. Yeah. When you look at the structure of these three components, you realize that they are all based on carbon. Okay, their structural formula is all based on carbons. Okay, you make the mainframe of it. Okay, let's look back at what is organic chemistry. Organic chemistry, okay, is all about the study of the properties, the preparation, the identification, as well as the modification of carbon-containing compounds. Okay, a lot of this here, we're going to in this subject we're going to learn a lot of understanding the properties of it. Okay, identify it and modify it. Okay, preparation, not really. Okay, you can get from natural ingredients. Okay, and sometimes you do have preparation as well, but mainly in these three areas. Yeah. In contrast, inorganic chemistry is a study of elements of non-carbon containing compounds. Okay, a lot of these are not really related. Yeah, this is very inorganic chemistry is those without the carbons contains. Yeah. A lot of this one is usually in the industry, chemical industry usually uses that. Food industry is concentrate more towards the organic chemistry. Yeah. Okay, looking at some of the differences between organic compounds and inorganic compounds, when you're looking at the bondings that we learned in chapter 2, organic compounds is usually covalent. Yeah, covalent. Inorganic is usually ionics. Okay. Forces between generally very weak, okay, because most of the compounds are through non-polar covalence here, so they are relatively weak. Okay, if you look at the intermolecular force, is towards the dispersion force. Yeah. Okay, dispersion force. This is quite strong because it's through ionic. Normal physical states, we got like gases, liquids, and low melting point solids. This is usually very high melting point solids. Okay, these are closely related. Okay, again, it got to do with how the molecules or the ionic compounds interact with each other. Yeah, so if just say that this is two molecules. Okay, two molecules, when the interaction between these two is weak, okay, you are easy to separate. Okay, a bit of heat or what, it can be separated. Okay, that's why it can change from one phase to another phase. But if it's inorganic components, these two are very strong. Okay, heating or whatever you require to heat until very high temperature, only you can break the bonds. Okay, that's why usually they will retain as ionic solids. Okay, solids. Usually it's flammable. Okay, it can break because of the weaker bonds. Okay, it can be break. Okay, to create energy. Usually this is very difficult to break the bonds. Usually we talk about the intramolecular forces. Okay, within the molecule. When it's difficult to break, okay, usually they have very difficult to be flammable, yeah, not non-flammable. Solubility in water usually is very, very low in solubility. For inorganic chemistry, inorganic compounds, they are often high because of ionic. The charges, this one is due to charges, yeah. Okay, remember water. Okay, when talking about water is polar. Okay, polar molecule. Polar molecule, usually these can interact through charges, yeah. Although here, they have a partial negative, partial positive charges, okay. And this slightly positive and slightly negative can interact with the positive charge and negative charge of ionic compounds. Whereas these, there's no charge, okay, they have very weak interactions, yeah. And sometimes they don't have interaction at all, that's why they cannot compatible, okay, which means that if you put organic compound into water, they are not soluble, they will just separate, yeah. Conductivity of water solutions, okay, non-conductors, usually when there are no charges, usually they are non-conductor. If you put electric current through, okay, it won't conduct the electrics, whereas this will conduct. If talking about reactions, okay, usually very slow, this usually very fast, yeah, okay. One of the reasons it got to do with the charges. Okay. Okay, identify each of the components as organic or inorganic. Alright, so as I say, organic is those with the carbon component. So this is no, yes, yes, no, yes, no. Okay. Okay, to study the organic chemistry, some of the tips here, very important is the naming. Know how to draw the structure, okay, make sure you know how to do this. Able to describe the physical properties, okay, like melting point, boiling points, solubilities. Then you need to know how to write the reactions, identify the typical uses of these organic compounds, yeah. Okay, let's look at 3.2. 3.2 is functional groups, the organization of organic compounds. Okay, let's look at this in a way here. There are thousands, okay, thousands of organic compounds in this world, okay. Luckily, these organic compounds, they can be separated into different type of groups, okay. These groups are based on what we call the functional groups here, okay. So when you look at the molecule, okay, when the molecule has a certain group in there that attached to it, okay, then we can classify based on that. Okay, as the name it tells you, these groups, okay, they have certain type of function. Okay, all of them they have a certain type of function or characteristics. Yeah, that's why we call functional groups. What are the functional group examples? The first one, this one, is usually the backbone. Yeah. Okay. In this chapter, chapter 3, week 3 content and week 4 content, we're going to concentrate more towards this, which is basically the backbone for the organic compounds. We got alkane, alkyne, and aromatics. Okay. So you can see from here, for alkanes, usually there's no function group. For alkene, they have what we call double bond, okay, one or more double bond, carbon-carbon double bonds. This we can triple bonds. Aromatic, we got 6 carbon, 1, 2, 3, 4, 5, 6, with alternating single, double, single, double, single, double bonds here. In this case, we call it as the aromatics. Okay, see, these are some of the examples of organic compounds. We got ethane, ethylene, okay, acetylenes, okay, benzene, and so forth. Okay, write the condensed structural formula for each of these following compounds. Okay, we also need to learn about, earlier I mentioned about what we call the condensed structural formula. This is the keywords that you'll be seeing again and again, both in the tutorial questions as well as in the exam questions here. When you see this word structural formula, okay, structural formula is a formula that can tells you the structure. Okay, if the formula doesn't tell you the structure, then you don't call it as a structural formula. Okay, so it's very important for you to understand the distinction between these. Yeah, when you talk about structural formula, you need to know the structure. In order to make it simple, you condense it. Okay, that's why it's called condensed structural formula. Yeah. So for example, in this you can see the structure. Okay. When you see the structure, you can see from here C with H. Okay. then you can condense in such a way, CH3, CH2, bracket 2, okay, these two represent this, and this. Alright, when the exam tell you to do the condensed structural formula, there's actually no right and wrong, as long as you can demonstrate in making it condensed. I'm fine with that, yeah. So if you really want, you can also do such thing. Okay, I won't penalize you, yeah. So for this same thing, you can see the structure. You can even see there's branches over here. Okay, then you can see, you can condense in such a way. This two you can see is to talk about this two. Okay, this three, you see the two here is talk about this two. Okay, this CH, this CH, CH3, yeah. Okay, so the condensed structural formula, you can see that you can still see the structure, yeah. Okay, what I mean by that, right, is that sometimes when you condense too much, you actually lose the structural formula, yeah. Okay, for example, if you condense this into C, how many are there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So you can see, you can draw like that. You condense all the way to molecular formula. Okay. But if you want to expand that, can you see the structure now? You can't see the structure because you do not know if I expand, I can expand to be like that. 1, 2, 3, 4, 5. Okay. So you can see from here, okay, that if you see C over here, alright, then if you condense, if you expand to this, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, see, you can draw in the straight line. Okay, not necessarily you become this structure. Okay, that's the reason, yeah. Okay, that's the reason you cannot condense too much to become molecular formula. Alright. Okay, some of the other functional groups you may see attached with the what we call the hydrocarbons, the hydrocarbon the backbones, yeah. So this functional group, for example, if I have the alkanes, okay, it can be attached together with and giving additional function to the molecule. Okay, so what are the other functional molecules? We got like alcohol group with the OH, phenol, okay, directly the ring attached to OH. Amine is where NHH, aldehyde, C double bond OH, okay. A lot of people, they confuse this and this, yeah. Okay, so you have to be extra careful. Ketones, okay, ketones is very related to aldehydes, okay. Just like this is the carbonyl groups is in the middle of the hydrocarbon chain, whereas this one is at the end. The carboxylic acid group is double bond OOH, okay. Ester is where they got this ester bond, okay. Ester is frequently in the fats and oil, okay. Amides is in protein, C double bond O and H, yeah. Examples how you can see from here, you can see proteins, okay. Proteins you contains like amide, you can see C double bond O and H, okay. This one is organic compounds because you can see the backbone, okay, is carbons. Alcohol, okay, ethanol, the one we use it for sanitization very frequently. You can see there's an OH group over here. Then you can see the aldehyde, okay, aldehyde and ketones is very common, okay, for carbohydrates. You can see glucose over here, which is an aldehyde. Fructose, okay, fructose is also a very common sweetener, okay, very sweet compared to glucose. And you can see a carbonyl group over here, yeah. Both of them please take note, they are both 6 carbon. Okay, some people they thought fructose is 5 carbon. That's wrong. Yeah, okay, we're gonna learn more about that. Then you see over here carboxylic acid. Very frequently you can see from the fatty acid. Okay, fatty acid is one of the component for oil and fat. Okay, then amino acid, you can see it also got the carboxylic acid group over here. Okay, so you can see that all these functional groups are all part of the main structure for the food components, the protein, carbohydrate, and lipids. Okay, the next section is, okay, we're going to talk about alkanes, yeah. So for this chapter, as I mentioned, we're going to talk about the backbones, okay, of the compounds. Is either it can be either alkanes, alkene, alkyne, or aromatic compounds. But firstly, let's look at the alkanes, yeah. Okay, alkanes. Alkanes is considered as saturated. Okay, when we're looking at these hydrocarbons, okay, what are hydrocarbons? Hydrocarbons are the simplest of all organic compounds, yeah. That contains only 2 elements, carbon and hydrogens. Okay, this is very obvious from the name. Hydrogen, carbon, yeah. Hydrocarbons can be classified into 4 classes: alkanes, alkenes, alkynes, and aromatics. So we can actually separate into 2 categories. Okay, for alkanes is actually saturated. For alkenes, alkyne, aromatic is called unsaturated. So what is these 2 differences? It got to do with the carbon-carbon bonds. Okay, the carbon-carbon bonds for saturated is single bond. Okay, for unsaturated it can have a double bond. Okay, carbon-carbon double bond, carbon-carbon. This one in this is aromatics. Yeah. The reason why is it called saturated, unsaturated is because if it's saturated, no other elements can be added into the bond. Okay, that's why it's called saturated. Unsaturated is when additional the elements can be added into the hydrocarbons. Alright, I'm going to demonstrate that later. Yeah. Okay, these are the very simple classifications. Okay, when talk about the alkanes, you can call it as it contains only carbon-carbon single bonds. Okay, when you talk about alkenes, they contains 1 or more carbon-carbon double bonds. Yeah, so you have to take note of this. It contains 1 or more carbon-carbon double bond, which means that some of the bonds can be single bond. Yeah. For the alkynes, it contains 1 or more carbon-carbon triple bond. This one benzene, right? As I mentioned, this carbon ring, okay, with alternating double single bond. Yeah. Okay, saturated hydrocarbons, okay, single bonds. You will see that the carbons, okay, they will attach to 4 different things. Yeah. Okay, they usually attach to 4 different things. Okay, why is it so? Please refer back to the previous chapter 2, because you can see that the carbon over here, it contains 6 outer shell electrons. Okay, 1, 2, 3, 4, and they will sharing, okay, the non-polar covalent bonds with the hydrogen, okay, to make it 8 electrons. Yeah. 8 outer shell electrons. For the alkanes, because from the name itself we have mentioned that it doesn't contain functional groups, as a result, right, it's very non-reactive, which means that if you try to react it with acid or with other components, usually they are not reactive. Yeah. So this is a structure. You can see that it contains a carbon-carbon bonds. Okay, and this we call as a tetrahedrals, and the bond gap between them is 109.5. Okay, this is how you draw the flat structure. Okay, and the 3D structure over here. Yeah. Okay, If you look at this, right, you see that the gaps over here is all 109.5. The reason, right, is that they would have the optimal is to have a gap between them. Okay, they will push apart to have this gap in them. Yeah. There are a lot of alkanes. Okay, as the number of carbon expanded, okay, they will have more hydrogen. Alright, these are the name of it. This is a general formula, CnH2n plus 2. So if you plug that, if it's only one carbon, okay, the n is 1, so it will be CH2 plus 2 equal to 4, okay, so it will be CH like this, okay. So it will methane. If it contains 3 carbons for alkanes, it will be C3. Okay, 3 times 2 equals 6, 6 plus 8, 2 becomes 8, yeah. C3H8, so it will be a propane, and so forth, yeah. Alright, the next one will be the naming. Okay, naming is one of the very important areas, okay. For naming, we got two handout 1 and handout 2. Handout 1 is will teach you more in-depth with examples of how to do the naming. Okay, come over here. Okay, so you can see over here they teach you. Okay, these are the what we call, when you start naming, you need to know about what we call the prefix here. If it's 1 carbon, we call it met. Okay, 2 we call it it. 3 carbons we call it prop, and so forth. Okay, unfortunately, for those who are not familiar, these need to be memorized. Okay, these need to be memorized. Okay, so first you need to find the longest chain. Okay, so the second step is to find the branch. Okay, the branch. Then the branch, these are the naming for the branches. Okay, usually exam will test you to prop you. Okay, so you must remember this. The branch name we call methyl. Okay, if it's a CH3, ethyl, if it's C2H5, propyl, if it's C3H7. Once you have that, you can start naming. Yeah. Okay, you can start naming. So it teaches you step by step over here. Yeah. All right. Then you got another handout. Handout 2, we talk about the priority. Okay, this is very useful when we're talking about cis and trans. Okay, for the alkenes. Yeah. Okay, because we need to base on the priority of the groups. Okay, let's look at this IUPAC naming. IUPAC stands for International Union of Pure and Applied Chemistry naming system for organic compounds. Consists of 3 components parts here. Normally is what we call common names here. Before there's a IUPAC naming system, there's what we usually use the common name. Okay. Because of the international communications purpose, so they actually created the IUPAC naming to reduce the confusion. Okay, so you see over here, usually we need to have the prefix. Okay, prefix denotes the number and then of the attached groups over here, the appendix. Then the root will depend on how many carbons are there. Okay, then the ending will depending on what kind of groups are there. Okay, give you examples. Okay, so you can see from here the naming alkanes always end with A and E. Yeah, if it's an alkanes, okay, which only contains single bond, we always end with A and E. Okay, for N. Okay, let's try this one. Okay, so you can see from here. Okay, there are a few steps here. Usually the first one is find the longest chain. To identify the appendix group. Okay, I call it appendix group here because it's a group attached to the main branch group. Okay, 3. Okay, the numbering. Okay, 4 step is start naming it. So the first one is longer chain 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, either way that's fine. Let's make it simple. 1, 2, 3, 4, 5. This is the longest chain. Okay, when it's 5 carbon is pen. Okay, then this is the appendix group. CH3 we told what is metal. Then we need number it. Okay, 1, 2, 3, 4, 5. Now the numbering, you need to make sure that the appendix group is the smallest number. Yeah. Okay, 1, 2, 3, 4, 5. So this appendix located at carbon number 2 and 4. So it will be 2,4 metal pentane. Okay, 2,4 metal pentane in this case. This one 5 carbon. Look at the appendix group. Okay, this is the longest chain. This appendix group, both located at 3. So in this case will be 3,3-dimethyl, okay, pentane. Okay, the answer will be here, yeah. Okay, 2,4-dimethyl pentane. This one will be 3,3-dimethyl pentane. Okay, the reason why you put di is because they are two of the same group. Okay, that's why you use the word di, means two metal group. Okay. Okay, let's try this. Draw a condensed structural formula. As I mentioned, structural formula is when you still can see the structure, just that you condense to make it simplified. So you start to draw hexane. After you draw hexanes, you place the appendix group, ethyl and methyl at carbon number 3 and 2. Okay, this is how you do it. You draw the hexane, okay, the methyl group at carbon number 2, the ethyl at carbon number 3. There are a few ways for you to represent the alkanes. Okay, of course, this is the condensed structural formula that I have mentioned again just now. This is a line structure. Each of this point is 1 carbon. Okay, 1, 2, 3, 1, 2, 3. Okay. Usually, I do not encourage to use this one because it's too simplified and usually you can get confused. This ball and stick model is using a 3D structure. Yeah. Okay. 3D structure is when we usually in the using a ball and stick models. Okay, 3D model to visualize the 3D model. Okay, the 3D structure. Okay, this one is very useful. Yeah. Okay. We will learn that more in the practical class. Okay. Okay, for alkenes, right, there's a certain conformation. Yeah, basic conformation is the what we call the how the arrangement in the 3D arrangement, the conformation. Okay, the 3D arrangement. Yeah, when you're looking at this, there are two ways that it can arrange here. This carbon, hydrogen, hydrogen. Okay, so C2H6. When you're looking at this, okay, the carbon-carbon bond here is actually flexible. It can be turned another way around. Okay, so you can see from here, carbon and carbon. Okay, it can actually twist. If it's a single bond, it can be twisted. Yeah. So if it can be twisted, right, which means that the hydrogen can either be in this staggered conformation or eclipse conformation. Okay, how you differentiate between staggered and eclipse is when you wheel. Okay, so this is you wheel in such a way. Okay, you wheel in this way. Okay, not in this way, you wheel from this way. When you wheel from this way, when the hydrogens, okay, are exposed, okay, when you view in here, you can see 6. Okay, you can see actually 6 the hydrogens here. Okay, so you put your eyes over here. Okay, you look through, you should be able to see 1 carbon and then 6 hydrogen. Whereas if you put over here, okay, you look over here, you only can see 3 hydrogen because the hydrogen at the back is totally being blocked. Okay, blocked by the vision. That's why it's called eclipse. Okay, for stagger and eclipse, so there are 2 possible conformations for these alkenes here. But which one do you think it will exist most? In this case, it will be staggered. Okay, as I mentioned, staggered is the most stable conformation with the lowest energy. Okay, as I mentioned, they always like to distance the furthest apart. If it's in the staggered, the hydrogen and hydrogen, the distance is very far apart. Whereas if it's eclipse, it's close by. Yeah. Okay, if eclipse is close by, that's why in this case staggered is more preferred compared to eclipse. Yeah. Okay, for the physical properties, okay, physical properties are like the boiling point, the melting point, the density, solubility, and so forth. When we're talking about the physical properties of alkenes, it's a non-polar compounds, okay, with very, very weak interactions between molecules here. So we're talking about one alkenes, okay, interact with another alkenes, usually is very, very weak. Okay, if it's very, very weak, it's easy to be separated. Okay, when it's easy separated, it will change from one phase to another phase. We're going to talk more about this in the Chemistry 101. Okay, if two of the molecules, they are very close to each other, packed one after another. Okay, all right. They will be in a solid state. When they are become the liquid state is when they weaken. Okay, the intermolecular force weakens. Okay, and start to go slightly around. Okay, and this is the liquid the state. If it's gaseous, is the intermolecular force is break even more, and then they will be very far apart. In this case, it will be in the gaseous state. Okay, it's all linked to the intermolecular force. Okay. So as you can see from here, the more carbons we have, actually they have more stronger intermolecular force. Okay, that's why you can see from here, if the molecules is only 1 to 4 carbons long, okay, so 4 carbon long, when they interact, it's very, very weak. In that case, they will be in the gaseous state. As you get longer, they have more stronger interactions. Okay, they will be in liquid state. When they are very, very long, okay, then when they interact very strongly, they will be in a solid state. Yeah. When you're looking at this, so before I continue density, that's why I always say, even though the interaction is very weak, but the more carbons you have, the stronger the intermolecular force. Okay, I repeat again, yeah. Even though the intermolecular force is weak between them, okay, dispersion force, but as the carbon number gets longer, okay, it will contribute to stronger intermolecular force. Okay, the density, okay, will increase through the molar mass, okay, which means that the longer the carbons, the more the larger the density. However, because of what, the density is always lower than 1. 1 is the density of water. Okay, lower density means lighter. That is why alkanes, if you place with water, it will always float on top of the water, not underneath the water. Yeah. So you can see from here, just to reiterate what I have mentioned, the longer the chain, okay, so when they interact with each other, the stronger. That's why you can see the melting point is increasing, boiling point is increasing as well. Okay, and they will change from they will not change. Okay, they will go from gaseous to the liquid state. Okay. How about if they have branch? Okay, branch is when they are not straight chain. Yeah. You can see from here they branch. Okay, branch chain and straight chain, although they got the same molecular formula, okay, they got the same molecular formula, but they have a different structure. You can see that they have an influence. The trend cannot be okay. The trend cannot be explained. Cannot be tallied in here. All right. But what you can know, what you can say that if they got a different structure, they will have a different melting point and boiling point. Okay, arrange the alkene in the following step in order of increasing boiling points. Okay, we got butane, decanes, and hexane. Yeah, so you can see the shorter we have a lowest. Okay, increasing order. Yeah, so we follow by hexane, and the last will be decane. Okay. Okay, last for the week 3. Okay, we talk about the cycloalkanes. Okay, it's very important. Yeah, a lot of people they confuse cycloalkane and aromatic. Okay, but there's also what we call the cycloalkenes. Okay, do not confuse. Alkane and cycloalkenes, the only difference is that the same difference made of carbon-carbon single bond. Okay, carbon-carbon single bond. Okay, you can see from here, they are all carbon-carbon single bond. Okay, the only difference, right, is that instead of a straight chain, they join together. When they join together, one of the bond, okay, means that the additional bond, which means that 2 hydrogen will be taken out. That's why you can see from here, the general formula is CnH2n, not +2. Okay, because it is impossible to add another 2 more hydrogen in there, okay, because it's being replaced by a single bond. So it can be either a 5-member or 6-member ring, which is the most common ones. Okay, right, we call it as a cyclopentane or cyclohexane. Yeah. So in this case, right, when we're talking about the cycloalkanes, they will have a different conformation. Yeah. Okay. Although the single bond, there's a free rotation. Okay, carbon-carbon free rotation. But when we're talking about the bond, we do not have free rotation. Okay, because the ring, over here is being restricted. It cannot turn. If it's here, it can turn around. Okay, but it's a ring, it cannot turn. In that case, okay, if you want to turn, you can break it, but require very large amount of energy. Yeah. In this case, then you have what we call the cis-trans isomers. Yeah. So you can see from here, if it's a cis-trans isomer, cis here carbon. Here we got hydrogen. Okay, in this case, okay, we got cis-trans isomers. When the two is the same, okay, we call it as a cis. If it's a different one up and down, we call it as a trans conformation. Yeah. How you determine whether it's a cis or trans? You need to look at the between the carbon, okay, and the carbon here. So you can see from here, before we know whether it's a cis or trans, we need to know the priority. Okay, so priority over here. So we always choose the higher priority. Yeah. So over here, you see hydrogens, okay, and CH3. So CH3 has the highest priority. So we need to choose this over that. So in this case, if we choose the CH3, not the H, you choose the CH3, not H. When these two is at the same side, we call it the cis form. Yeah, again, here you choose which one is the highest priority. This one has a higher priority, this one has a higher. In this case, if it's up, one, down, okay, different direction, we call it as the trans conformation. So in this case, identify each of the following cycloalkanes as cis on trans. Okay, in this case, this is trans, one up, one down. Okay. Carbon. Okay. So same direction. Okay, we look at the priority. Choose this one, cis. Okay, so here is the hydrogen. Okay, when there's no writing, right, it's carbon and hydrogen, yeah. So in this case, okay, priority is this, so same direction is cis. Okay, take a break now. Okay, if you want to continue, you can continue to week 4. Okay, if not, come back another day. Okay, for week 4 content. Yeah. Okay, let's look at week 4 content. Week 4 content, we talk about the unsaturated hydrocarbon, the alkenes, the alkynes, and aromatic compounds. So let's look at the alkenes. Alkenes is the definition is that it contains one or more carbon-carbon double bonds. Okay, for alkenes. So for alkenes, you can see that in this case a simple one. You got 2 carbons here. There's a double bond, hydrogen, 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 hydrogen. Yeah. In this case, we only got 4 hydrogen instead of 6 hydrogen compared to alkenes. Okay. Because one of the hydrogens, 2 of the hydrogens are replaced by the one of the bonds over here. You see that the distance has increased compared to the alkenes. Okay, again they want to distance apart with each other. Okay, so in this case 1 to 20. The naming is exactly the same as the alkenes. The only difference is the ENE, which is a double bond. The longest chain, okay, need to include the double bond, okay, so it cannot be in this way or this way. You need to contains the double bond together and make sure that the double bond has the lowest number. Okay, in this case you cannot go from here, you need to go from here because the double bond need to have the lowest number. So 1 2 3 4 5 6 6 is hexene, okay, with a double bond. The double bond is located at carbon number 1, okay, over here. The metal grade is carbon number 4, okay, so it's 4 metal 1 hexene. Some people say that you can actually write 4 metal hexene, okay, that's fine as well, yeah. Okay, let's practice this. So we got 4 carbons, 1 2 3 4, or 1 2 3 4, that's fine. Double bond located at carbon number 2. Okay, so in this case will be put for 4. Okay, double bond butene. Okay, you can write there the double bond located at carbon number 2. Okay, so it can be a 2 butene, 2 in. That's fine as well. Either way, that's fine. Yeah, no penalize you. So here in this case, you need to include here the lowest number. Okay, 1 2 3 4 as well, the same. In this case, is 4 carbon, so it's but. Okay, so will be butene as well. Alright, in this case will be 1 butene. Okay, looking at carbon 1. This appendix is looking at carbon number 3 is tritene. Yeah. So in this case, you need to include 5 is pentene. Okay, so the ethyl group is looking at carbon number 2, so it's 2 ethyl 1 pentene. Okay, that's fine. Okay, so this is the answer. When you're talking about the physical property, is very similar to the alkenes. Okay, the longer the chain, okay, also dispersion, the intermolecular force is also dispersion force. It's a weak force, but as you get longer chain, it have a stronger interactions. Because of stronger interactions, so you have a higher boiling point and higher melting point. Yeah. Density again is always lower than 1, okay, which means that lighter than water. Yeah. So same thing over here, the longer chain you will be in a different state, while the shorter compound is always gaseous, the longer will be liquid. Again, those that's 18 carbon and above will be in a solid wax-like solid state. Yeah. For this, okay, the low molecular weight one is always unpleasant smell. Yeah. Yeah, because it's volatile. One thing is because it's volatile and it's easily interact, evaporated and go to your nose. So when you smell, it's actually very stingy. Yeah? Alkenes, because of double bond, they have restrictions. Yeah. So imagine this is a double bond. Okay, single bond you can go around. Okay, but when you got double bond, you cannot go. Okay, unless you break it. So in this case, there's a restriction in the rotation. So we have the cis and trans conformation. Okay, the priority is this. This same directions. Okay, will be in the cis form. Yeah. So this is we got the cis and trans configurations. Okay, you can see, although they got the same molecular formula. Okay, both is H8. Okay, C4. Okay, C4H8. Okay, but because of a different conformation, one is cis conformation, one is trans, you can see that they have a different melting and okay. The trend I cannot tell you. It really depends on the molecular structure. Yeah, the only thing you can say is that they will have a different physical and chemical properties. Then you need to test it out or go and find the information regarding the cis and trans configuration. Yeah. Okay, let's try this. Okay, which one exhibit the geometric isomerisms? Okay, draw the structural formula. Geometric isomerism, in this case we are talking about the cis and transformation. Okay, so to make your life easier, okay, it's asking you can exhibit, which means that it can have a cis trans or not. Okay, it can whether have a cis trans, not asking you whether this is cis trans or trans. Okay, so to make your life easier, you can draw this. Okay, just it's the same thing, just that it looks nicer. Okay, so in this case, it can be either that or that. Okay, so you got a cis, you got a trans. So the answer for this is yes. For this is cis. In this case, please remember, always if there's one side is always the same, okay, there won't be any cis or trans. Okay, you don't say that, don't tell me that, oh, I compare this and this, cannot. Okay, whenever there's the same thing, you cannot have cis and trans. In this case, I can have that, or I can have in this case cis, or this one is a trans. Okay, so the answer is here. Alright. Then we have a cycloalkane as well, same as a cycloalkane. Okay, in this case cycloalkenes, okay, they have a double bond in the ring form. Yeah, also same thing, the formula, they have less 2 of the hydrogens. Okay, for the cis trans, it is not possible to have the trans molecule with 7 or less carbons here, because you can see from here, if it's a cis, okay, still okay, but if the trans, there's a constraint. Imagine the ring is smaller, okay, it's almost impossible for you to twist until in this conformation. Yeah, so for cis trans conformation, the molecules to exhibit cis and trans, the cycloalkenes need to be 7 or more. Yeah, okay, not to say that it's impossible, it's possible to have it, just that it's unlikely. Okay. 3.6, we talk about alkynes. Okay, alkynes is in definitions is one or more carbon-carbon triple bonds. It's very similar compared to alkenes. Okay, the only difference is that now it contains 3 carbon-carbon triple bonds. So again, there's less 2 hydrogens. Okay, altogether less 4 compared to alkenes. Okay, because it has been replaced by a bond. In this case, the carbon, the dimension, the angle will be 180, because as I say, they will try to maximize the distance between the elements. Yeah. The naming is very similar. The only difference is that for alkenes, E and E for alkenes, this is Y and E. Yeah? So same thing, you need to include this in the longest chain and the closest. So we go for 1, 2, 3, 4, 5. Okay, so we got the 5 and the triple bond located at carbon number 2. So it can be 2. Okay, pen time. Okay, you can pen 2 in. That's fine as well. Okay, either way is fine. No penalize you. Yeah. In this case, 1, 2, 3, 4, 5, 6. We'll go at carbon number 5. So it's 5 metal. Okay, 1, 2, 3, 4, 5, 6. 6 is hex. So will be located at carbon number 2. So will be 2 hex sign. Okay, it's the answer for that. Okay, the last section is aromatic compounds. Okay. Okay, by the way, for the alkynes, okay, the physical property is exactly the same. Yeah, the longer the chain, okay, the higher the melting and the bonding point. The density also will be lower compared to water. Yeah. Aromatic compounds, okay, the last one. Always remember it has a benzene ring. Okay. It's highly unsaturated because of it contains a lot of the double bonds in there. Okay, so for benzene ring or aromatic compounds, it will always have 6 carbon. Okay, 6 carbon, and the alternating double, single double bond. Okay, you can either draw this the full structure, or you can draw this 1, 2, 3, 4, 5, 6 and around here. Okay. For the benzene ring, usually is in the inorganic the industry. Okay, in the solvent as well. But you do able to see some in the food context, like for example, amino acid. You can see they have a benzene ring. Vitamins, you can see a benzene ring as well. Okay. Alright, so that's it for the week 4. Okay, these are the summaries. Okay, so that's it for week 4. Again, please comment in the Padlets, okay, whether you have questions or no questions. Okay, please make sure you comment it in the chapter 3 columns. Okay, please remember to put your student ID as well as your name for attendance taking. Yeah. Alright, thank you very much.